I want to close out this discussion of the indefinite integral with some properties of, of the definite integral. Indefinite integral is coming up. Properties of the definite integral. So, and these are fairly simple and straightforward. Let's see, if c is a constant in each case below, and a is a constant too, a and b are the limits. This says the definite integral from a to a of a function is equal to 0. Well, a to a, how does that work? Well, if you think of this geometrically, right, you know, if we're looking at the graph of some function f over, you know, it's continuous, let's say, and right here at a, you know, the upper and lower limits are the same, so interpret it in terms of the area, but the area under the curve here is just a line. There is no area, right? This is just a line. There's no area. We'd have to go from a to some, you know, b to get some kind of area, so that the integral would be a non-zero number. So obviously this makes sense that the integral would be 0 if the upper and lower limits are identical. And if you think about it, the delta x in our limit definition, right, is the length of the interval, which is 0 divided by n. So you're multiplying everything by 0. All those rectangles, you know, there are no rectangles technically, but you'd be multiplying by 0 in the formula. Here's another one. The integral from a to b of a function f is equal to -1 times the integral from b to a. So basically what this says is changing the, swapping the limits of integration changes the sign. And that should make sense because, again, if you think of delta x in that definition is b minus a over n, okay, well, if I swap the order, right, then I'm going to have a minus b, which would be -1 times whatever delta x is. So let's just suppose that b is bigger than a. Let's just say b is 5 and a is 1. 5 minus 1 is 4, but if I go in the other direction, right, 1 minus 5 is -4. And so you see that's where that negative comes up from so all the delta x's would be equal to a negative number. The integral from a to b, c is a constant, remember, of any constant is equal to c times b minus a. And that comes from the fact that if I look at a function over an interval, say from a to b, we'll let b be bigger than a, and I look at a constant function. Now what's the graph of a constant function look like? Well, it's a horizontal line, isn't it? The output for any input is equal to c, and so we just have this horizontal line. Right, that would be the function in that case. And in that case, assuming c is positive, as I've drawn it here, the area under the curve from a to b would indeed be a rectangle. Right? And the area of a rectangle is the height, which is c, times the base, which would be b minus a, and hence that's where we get that from. The integral from a to b of f of x plus or minus g of x is equal to the sum or difference of the corresponding individual integrals. And I think that kind of makes sense. I hope that makes sense, that you can add and combine those. Similarly, if you have a constant times a function, that constant can come outside of the integral. The function cannot come outside of it, but the constant can, constant multiple. So these two properties are the linearity properties, and they come directly from the linearity properties of sums that we've looked at. So in the limit definition, right, we were talking about a summation before we take the limit as n goes to infinity, and these properties come directly from that. So we use these all the time. Okay. So for example, what if I wanted to find this integral here? I can use the properties above to do that. And the first property I'll make use of is right here. If the integral, if I'm adding two functions together, I can break them up into sum of two integrals. So I have 4x cubed plus 3. I can write this the integral from 0 to 2 of 4x cubed plus the integral from 0 to 2 of 3. I should put my dx in each of these, right, to tell us the variable of integration is x. Okay. Now, this first one, 4, is a constant multiple. I can pull that 4 out, and I get the integral from 0 to 2 of x cubed dx. Okay. Here's 3 is a constant, so I can make use of this property, right? And if I have an integral from a to b of a constant, it's the constant times b minus a, which is the length of that interval. So in this case, this would be equal to 3 2 minus 0, or 3 times 2 is obviously going to give me 6. Now, this one right here, the integral from 0 to 2 of x cubed dx, we would have to compute, right, like we actually did this one in the last video. We did this one in the last video, and this came out to be equal to 4. We used the limit definition. Okay, and this is from the previous problem that we did, that we solved. Okay, so you can go back and look in the last video for that one. At any rate, what are we going to get? 4 times 4 here is 16, 3 times 2 is 6, and we get 22. Okay. Now this is not the way we will be always doing this definite integral. We'll obviously talk about the fundamental theorem of calculus later, but this is idea getting used to these things. Here's another one. If the integral from 1 to 6 of a function is 8, and the integral of 1 to 6 of another function, g, is -3, find this expression. What's the integral from 1 to 6 of 5f of x minus g of x dx? Well, I'm going to make use of these linearity properties right here. So first of all, I can take the integral of a difference as the difference of the individual integrals. So it's 5 times f of x dx minus the integral from 1 to 6 of g of x dx. And then this 5 is a constant multiple here. I can pull that 5 out. Notice it only comes out of here, not over here, from the second integral, right? And now I can just replace the integral from 1 to 6 f of x dx. What is that equal to? The integral from 1 to 6 f of x dx is equal to 8. This whole thing here is equal to 8. And the integral from 1 to 6 of g of x dx is equal to what? Is equal to -3. And so I'm just going to get 5 times 8 minus a -3, which is 40 plus 3, or 43. Okay. Just a few more properties of the definite integral. Here's a real important one that we can use a lot. And this says that the integral from a to c of a function plus the integral from c to b of a function is equal to the integral from a to b of the function. Okay. Now, let me draw a picture that might help illustrate why this is true. I'm going to assume that a is less than c, and that c is less than b. It doesn't have to be like this. Remember, the value of a doesn't have to be less than c. The value of c does not have to be less than b. You know, just because a is the lower limit doesn't mean a is less than c. But I'm going to assume it's that way. Okay. And if I have some function here, let's draw some continuous function f, then the integral from a to c, this first integral, would be the area under the curve of the function f from a to c. It would be this right there, right? The integral from c to b then would be this area. So if I add these areas together, what's that going to give me? The area from a to b, and that's what we're getting with this. Okay. The real key to this is that the upper limit here of the integral on the left matches the lower limit of the integral on the right. So these have to match. These must match. And then the resulting integral is going to be what? The lower limit of the integral on the left, a, and the upper limit of the integral on the right, b. It's kind of like those c's are canceling out in a sense, you know, thinking about it. So here's an example. If I know for the function f that the integral from 2 to 5 is -12, the integral from 0 to 5 is +5, and the integral, we'll find the integral from 0 to 2 then. Okay. Well, notice, to get in this form, one way I can think about it is if I go from 0 to 2, the one I'm looking for, and then if I add the integral from what? 2 to 5. Since the upper limit here is 2, remember I want to match the lower limit, 2 here, to 5 f of x dx. Then in that case, by this property here, right, this b is equal to what? the integral from 0, the lower limit here, to 5. And I can now plug in the values I do know. The integral from 2 to 5 is negative 12. And the integral from 0 to 5 is positive 5. So our integral plus a negative 12 equals 5. And therefore, our integral from 0 to 2 f of x dx is what? 5 add 12, right? Which is 17. Okay, so a very useful property that we can make use of in various ways. Just a couple more now, just in closing. If a function f is greater than or equal to 0 on the given interval, then the definite integral from a to b is going to be greater than or equal to 0. And so we understand that also to represent what this integral then represents the area under the curve. So that's only if it's greater than or equal to 0. Remember, if it goes below the x-axis, it becomes negative, and that kind of is considered like negative area. And we're only going to for a and b not equal, then this definite integral will only equal 0 if the function itself is the 0 function. If the function f of x is always greater than the function g of x on an interval from a to b, so the graph of f is always above the graph of g, then I think it makes sense that the integral, right, of f of x from a to b is going to be greater than or equal to the integral of g of x. And finally, if the function f of x on the interval from a to b is between some fixed lower number, I'm calling that m, and some fixed upper number called capital M, then the definite integral of the function will be trapped between these values. And I'll illustrate that with this picture here. We'll let this right here be the graph of the function f, and let's go from 1 to 5. And on the interval from 1 to 5, the lowest the possible value for this function is, let's see, right about there, right? If I come across, then, and you might say that's about what? This is 10, 20, it might be 14. I'm just going to call that the m. I don't know. Maybe it's 14. Okay, that's the little m. That's the lower number. So all the values of the function just on the interval from 1 to 5 now, right? I mean, back here it might go down and get lower, but between 1 and 5, just on that interval, and little m is the smallest. And what's the biggest? Well, the peak looks to be right here. And so let's see where that is about. Maybe that's about 26 or something. I'm just going to call that big M, right? And so this means that our function from 1 to 5 f of x dx is trapped between what two numbers? Well, from b minus a in this case, b minus a is b is 5, a is 1, is 4. And so this is less than or equal to b minus a times big M, which is 4 times big M, and this is 4 times little m. Now, if you knew, if you want to estimate m is 26 and little m is 14 or whatever, you can plug those in and get actual quantities, but sort of trapped the value of our integral between two values. Okay, so these are the properties of the definite integrals. I want you to be familiar with them and be able to do manipulations like we've done. And as we learn more about the fundamental theorem of calculus later, we'll incorporate these properties into our work.